weak acid equilibrium, we cannot just use the concentration of the acid as H because it doesn't break up 100%. So the first thing we want to do is write the dissociation reaction. And it's really very simple. You write the acid, and then you just remove the H, and then write down everything that's left. And notice that we have a double arrow because it's at equilibrium. Let's go ahead and write an equilibrium expression. And so we have our acid and our OCl minus, the conjugate. These are both the conjugate acid and conjugate base. And then we have our initial acid, our original acid, and that's going to equal to Ka. And notice that they give us a Ka value. So then this is pretty much a Rice equation. So we have Rice tells me that initially that I have a molarity of 0.00125 molarity and none of these. And so again, what our change is minus x and plus x and plus x. And so at equilibrium, we're going to have 0.00125 molarity minus x and then x and x. So in the process, we need to then plug all this in. And so I know that Ka is 3.5 times 10 to the minus 8. And then H plus, we notice, is x, and OCl is x, so we can just say x squared. And then the HOCl is 0.00125 minus x. But notice, especially in a weak acid, that the Ka is very small, which makes us be able to delete the x. So we can omit this, which then makes it very easy to solve. You're going to see that pretty much when I do a weak acid solution, I'm going to do x squared over initial is equal to Ka. And that initial concentration, the I, is going to be for the initial concentration of the original acid. So then we can easily plug and solve. And when we solve this, I'm not going to take the time to show you plugging it all in. But if we move this around, if we multiply these and take the square root, we end up with x equaling 6.61 times 10 to the minus 6. So I know that that's what x is going to equal, is 6.61 times 10 to the minus 6 molarity. Well, if you notice, what is x? Well, x is H. So if I minus log this value, if I take the minus log of it, that's going to give me pH, which comes out to be 5.18. So that's the final answer for number 3. Now, pretty much the same thing for a weak base. And so what happens in a weak base is that we have this compound, so we have NH3. But it's very important to go ahead and write the water down, even though water's liquid, will not be in the equilibrium expression. But it helps us see the Bronsted-Lowry transfer. So in this case, water's actually acting as an acid, donates the H. And so NH4 picks it up. But then if this loses an H, what remains is OH minus, and then that keys out that that's a base. So if we write, again, it's at equilibrium, the equilibrium expression is going to be NH4 plus, the conjugate acid, conjugate base is OH minus, and on the bottom we have the original base, NH3, and that's going to equal to Kb. Again, it's a Rice equation. But you're going to get to a point where you really won't use them that much because you'll just kind of do x squared over initial. So I know that I have 0.00125 molar NH3. These are going to be 0. We're going to minus x plus x and plus x. And so for our change, and so at equilibrium, 0.00125 molarity minus x, and then x and x. Notice I'm not doing anything with the water. So then if we plug in, again, we're going to have x squared over 0.00125 molarity minus x equals Kb 1.8 times 10 to the minus 5. Same deal, very small, it's a 10 to the minus 5, so I'm going to omit the x. So then I can solve, I'll multiply 1.8 times 10 to the minus 5 times 0.00125. Take the square root, and so in this case, I'm going to end up with x. So I'll go ahead and kind of work this a little bit. You can kind of see where this is coming from. 0.00125. Take the square root, and that's going to give me x. And so the value of x in this case comes out to be 1.5 times 10 to the minus 4. Well, what is x? Well, x is OH minus, and it's also NH4 plus. I really don't care about the NH4 plus, because if I minus log this, then that's going to give me P, Px, POH, and so POH comes out to be 3.82. Well, I don't want POH. Very rarely do we use POH, so I subtract that from 14, and I end up with 10.17 is my pH. And being that this is a basic solution, I always kind of do that little double check. Is it a basic pH? And it is. It's 10.17. So that's acid and base, weak equilibrium calculations of pH.